So we are right at the part where we get to draw out the electron configurations. Some people prefer to use boxes, other people prefer to use lines. I am personally going to stick with the lines because they're a little bit easier, to draw than the boxes. But either way kind of goes the same way. So the way basically this goes is you pay attention to the valence electrons themselves. And I'm going to focus on the valence electrons for the type of drawings, not only the examples here, but also the ones in the homework. And let's start with nitrogen. Nitrogen has the 2s2 and 2p3 valence electrons. Now, each one of the orbital types that we have present represents a kind of orbital that we need to draw boxes for. Now the s orbital, if you remember, only contains one kind of orbital. So we only need to draw one box for the s orbital, but the p orbitals contain 3 boxes. The d orbitals contain 5 and the f's contain 7. And if you kind of remember it that way, s, p, d, f, and if you go in increasing order of odd numbers 1, 3, 5, 7, you're basically going to get the right amount each time. But as far as drawing them, what you need to do is draw that number of boxes. S has only one box associated with it. It doesn't matter what energy level it's in, it's only going to have one box. And the P's will have to have 3 boxes associated with them, also irrespective of the energy level in which they are. If you have a p orbital, you're going to have 3 of them. If you have a d orbital, you're going to have 5 of them. If you have an s orbital, you're going to have only 1 of it. And if you have f orbitals, you're going to have 7 of them. Alright, now what we're going to do is we're going to distribute the electrons present in each group. The 2s group has 2 electrons. One of them has to have spin up and the other one has to have spin down. So we basically draw the first one spin up with the up half arrow, and then we draw the next one with the spin down. And that basically accounts for the 2 electrons present in the 2s orbital. For the p's, here's where we actually use Hand's rule. Hand's rule says that if you have orbitals of the same energy, and you know that to be true if you're dealing with subsets of the same orbital, so the p has 3 subsets present, the d has 5, the f has 7, all of them will be the same energy. If you have orbitals of the same energy or boxes of the same energy, and you're putting multiple electrons in them, you're going to place them such that first, each box contains a single electron, no more than a single electron. So you have 3 electrons here, so what you want to do is place one in the first box, place the second one on the second box, and place the third one on the third box. Notice that each box has 1 electron with the same spin. All of these electrons are all of them are top spin, so they're all pointing up. Alright, so that's the way you would draw this. Now for the next one, it's a similar picture. You have an s orbital and then you have a set of p orbitals. This time on the third energy level. The first one, which has 2 electrons in the s, has 1 spin up, 1 spin down. And then for the 3 p's, you place one first on the initial box on the left, another one on the middle one, another one on the last one, and all of them are spin up, spin up, spin up. Once you have finished grouping each individual box with a single electron, you go back to the left and you start pairing them up with down arrows, right? So down spin electrons, in other words. So you have 1, 2, 3, 4, and 5 down spin. Okay, so at that point you have 5 electrons. Now for nickel, you have the 4s2 and the 3d8. So you're going to need 1 box for the s, but you're going to need 5 boxes for the d. And notice that for the d, since we have 8 electrons, first the way you draw this is to put 1 electron spin up on the first box, 1 spin up electron on the second box, 1 spin up electron on the middle box, 1 spin up electron on the second to last box, and another spin up electron on the last box. That accounts for 5 electrons. And at that point you come back and start pairing them up with spin down electrons until you have accounted for all 8. Okay, for arsenic, same idea. You have an S group, a D group, and a P group. So you'll have 1 block for the S, 5 boxes for the D, and 3 boxes for the P. And when you do these drawings, I highly recommend that you leave some noticeable space between the groups, because otherwise it becomes rather difficult to tell where it begins and where it ends for the specific groups. So definitely leave some space in between them to make it obvious that the group has ended and a new group has begun. Okay, for arsenic, we have 2 electrons on the S, 3 electrons on the D. That means that you basically have spin up, spin down for every single box in the S and the D electrons. For the P, you only have 3 electrons, so once again, 1 spin up on the first, 1 spin up on the middle, 1 spin up on the third one, and basically that's it. I really can't overemphasize the fact that if you draw this thing with a spin down electron on one of the inner boxes, or worse yet, 2 spin up electrons on any of the inner boxes, that would be a bad situation. That would be totally wrong. You'll be basically violating Hund's rule. Alright, now for rhodium, we have the 5s2 and 4d7, so you have 1 box for the S, 5 boxes for the D. And for the D, you have 7 electrons, so you start with the spin-ups. 1, 2, 3, 4, 5 spin-ups, and then you come back and you place 1, 2 spin-downs to end up with 7. And basically, by doing this, you have come up with the drawings for the electron configurations of the valence electrons of each one of these neutral elements. Alright, now what I want to show you next is the configuration of ions. But I'm going to save this particular section for the next video, and I'm going to couple it with the exceptions as well. So that will be the last video. So at this point, let's stop right here and continue on to the next video.